Thanks for coming back. There's one thing I want to clarify. I did this in a confusing way, so maybe I should explain a little more. So let's say we set AS. Let's just do this in a completely varied setting. AS means the connection is equal to our RS, the fiber dimension. We don't care about the variability in the phase direction. Okay. Then we can just write down the families that we have, which is just AS plus sections of S plus U is I omega sections plus some S minus some this is the triple bundle over E. Yes. Okay. So we can just do this. Just do the family set. This is. Then the family modulus is just the inverse image of beta so and it has a circle action. Then we can define. We can further portion of by H action. Okay. All right. So we have this moduli space. We have this portion by the constant H group. Okay. Now, what can we do about it? So now suppose we have a now we consider the following thing, even as delta, delta, delta. So one thing we can do is the following. We can consider C1 as S delta minus I and 3 pi delta. Okay. So I treat this as okay. This is a homological class, but I can represent it by harmonic forms. So what do you assume? Okay, it's very well. Okay, so given this, we have to take function. The C has delta delta, which is a factor of this H class. How to define its section? It says B to so we're going to do okay. So C1 must have delta E minus I over 2. So this is the homological class in H2B, right? So we represent it by a harmonic form. This is another harmonic form. This is another form W. So we take the difference another form. Then we do projection. This projection is the most often projection to the space of harmonic forms. The other is the space of it's just the orthogonal projection to us to harmonic. Okay. So this provides us with a section of this vector bond. And we say it's triple is admissible if this section there is no variation.
And Jianfeng, I'm slightly confused about this here. Isn't that now different than what you wrote here on the right? Because right here we have like a B, a solution here is a B worth of solutions, right?
No, I mean, let's see. So a solution is, let me see. A solution is, okay, that's what I'm saying. A solution is a B versus of solution. Okay, something here is something you have a collection on every beat, right? Then a solution. Okay, that's okay. All right, sorry, this is. I think this is. I don't want to. Okay, let me go to the question. This may not. Only okay. Yeah, this is okay, but this is may not be.
This is the very point from the end of the lecture.
Yeah, this is the point. Yeah, this is exactly the point. I try to write it in a more family setting, but
it's a different object.
It's a different object. It seems like. Okay. All right. Yes. Okay. So let's returns. So yeah. For now, let's ignore this. Let's the whole. Sorry. And now, okay. So let's have admissibility condition. Any question? So we say this is admissible if this section is no dimension. And now the fact is that if this triple is admissible. Then that implies this moduli space has no reducible solution. And that means is your action is free. Right? And now if we put another, if we assume this GQR generic, little work through here to get transversality, then we know that this amplitude of SW is a compact manifold dimension of this amplitude of SW. This is defined in the dimension of this S theta. It equals the expected dimension of it's just dimension of the base plus the expected dimension for the family cycle moduli space in single fiber.
So are you indicating here that we need G tilde and eta tilde to both be generic, or are you just not?
When we pick any P, then we pick a generic.
Yeah.
Then this is this dimension of P C1 of S P square minus 2 and minus sigma and so this is the index formula. That appears yesterday.
So you said that initially that B is probably infinite dimensional, right? What is the dimension B?
Dimension of P is the face.
Yeah, you said initially that the B might be infinite dimension.
Well, here let's say let's focus on finite. Let's assume that B is finite. Yeah, because if you let's say yeah, let's say B is finite.
It's still true. It's
Okay. Yeah, because in the end, so usually, for example, when we try to study, when we say B, when we say B equals the moduli space, we just do some truncation.
B and that.
You can make it a math.
Are the admissible triples also generic in the
That's a great question. So you mean the admissible triple? I mean, this is another generic relation.
right? So are you like picking a generic one among the admissible triples?
Yeah. So first we need to pick admissible and the generic.
Oh.
Admissible and the generic. This will be a manifold with 3 U1 action. Then what we can do is the following. Okay. So what can we do? Now we have a principal bond. Okay. Right, and let's give we can take the associated complex line number. Then what do we do? Oh, that should be plus. Okay. Wait. Okay. Yes, you have really need the dimension of this. No, this guy. Then what do we do? Then one thing we can do is okay, so we just take this MSW, this is oriented by orientation on this eight customers. Okay. Then if this bundle is oriented, if this bundle is oriented, then you can get only computation on this Seiberg-Witten moduli space. Then what do we do? Then one thing we can do is the following. Okay, consider. Now let's consider the fundamental class of this SW. This is a homological class, and we can do a direct product E1 L with L of K. Yeah. Okay. So this will be our homology. Okay. Then remember that MSW has a natural projection method, because really this is just the union of the moduli space over each fiber. So there's natural projection. So we can define the Seiberg-Witten invariant of this S tilde, G tilde, beta tilde to be defined to be written. We take this, take the control and 0, C1 K L. Python. Python. C1 K L. F and we have the 0. Of K Yeah, U is a formal variable, so this will be an element in H north star B. The formal variable. Okay. So, in other words, we get like the sequence of homological classes from the base. Okay. For each species structure. Now, there's a fact. So by standard, if all this is not make now that's the following. Okay, so this is not satisfying enough because we pick some G and E. And we really want a smooth invariant. So we want to understand how this invariant depends on G and E data. So so to do this, we make a definition. Let's say space, if let's consider a space of no variation. Sections of H class. Okay. Let's consider the space. Oh, let's consider the space of nowhere vanishing sections on this H class bundle and take pi 0. Okay. This we define to be the set of chambers. Okay. In other words, a chamber is just a homotopy class of nowhere vanishing section. It's H class. Now, standard homologism argument tells us that FSW, D and D, S theta, G theta, theta theta only depends on the C on the chamber. Definitely. So if two admissible G and eta give sections which are homotopy to each other, then you can use a standard homologism argument to show that the family Seiberg-Witten invariants are the same. So this allows us to say so. We can run. These are the methods we can FSW of E, E, then we spin C structures and change. Okay, the C is just a change. So of course, if you change different chambers, for example, if you go from one chamber to the other chamber, this homological class will change. Okay. There is a family version of wall crossing formula, which was first studied by TJV and IPU. So they try to understand some question motivated from algebraic geometry using the family Seiberg-Witten theory. And starting wall crossing is a crucial part of the argument. Okay. So, but for today's application, we'll just focus on the simplest case. In particular, so for let's assume to make our life easier, let's just focus on the simplest case for now. Let's assume first p plus x is greater than the relation of p plus 1. Okay. So this tells us, so that implies there is a unique channel. Okay, so this is that thing, and the second thing is I'm also going to assume this dimension of the moduli space equals 0. So that means in this case, the family is Seiberg-Witten invariant. Okay. Since E over V as Furuta is really just a number. Because you are just okay, in this case this is 0 manifold. The only thing left to contribute is the k equals 0 case. Then you are just counting points. Okay. So let's think about this solution a little bit. This means what? This means E as theta E, and you should have it next to equals negative dimension. Okay. Right, because this is divided in the sum of this. So we are in the following situation. If we think about a single fiber, okay, the expected dimension is negative, meaning that for a generic choice of metric and perturbation, the modular space is just empty. Okay. But here we are whole family. We have a whole family of manifolds. Then this dimension of then what happens is that occasionally on some discrete fibers, there are some discrete solutions. And we can just count them as an invariant for this family. Okay. So in other words, on generic fiber, there is no solution at all. And on finitely many fibers, there is a solution. Okay. And we're just counting these discrete solutions with some. That gives us a number which serves as an invariant for this family. We will also consider a more complicated version of this family Seiberg-Witten invariant and also family Bauer-Furuta invariant a little later. But for now, let's do one application of this invariant. So application. Any questions? Yeah.
In the definition of FSF, why would you need to have a U in the definition?
Well, you could also say that you get a sequence of invariant parameterized by K.
Right.
And that's fine. It's just a way to organize this data because, for example, when you want to do like family gluing theorem, family word processing theorem formula, family blow up formula, things like that, it's more convenient to write down this formal variable. It's yeah, you can view it as a generated function.
And also, can you also just interpret this as like homology and influences if you want to over?
Oh yes, okay, yes.
I will be confused. So in the simplest case where say B is S1, and this data is this already encoded in like the action? So it's given by some diffeomorphism of X.
Yes.
So is this family Seiberg-Witten invariant already? Is it encoded in the action of the diffeomorphism on like the proper Fred flow map, like dash and
Exactly. Yes, that's exactly the point I'm going to make now. Yes. So I'm going to do one application about pi zero of this. So that's what I'm going to do now. Okay, so let's see one application. So it's so we'll say given S X say F is exotic diffeomorphism is F is smoothly topologically isomorphic to identity, but F is not smoothly isomorphic. Okay. In other words, F represents a non-trivial kernel. Represent a non-trivial element in the kernel of zero diff to tau zero of home. So, yeah, and so on four manifolds, so well, as one application, we are going to be to discuss organized function of exotic. Okay, so the first exotic diffeomorphism of four manifold is discovered. Daniel Ruppmann, he used the family Donaldson theory and also gave he gave two proofs, one using family Donaldson theory, one using Seiberg-Witten theory. So we are going to do the Seiberg-Witten proof. Okay, so how does this work? So we take four manifolds x0, x1, simply connected, and it's such that, well, let me just list the conditions we want. First, simply connected, of course. Second, x0 should be homomorphic to x1. Okay. And third, Seiberg-Witten invariant of x0 S0 is different from Seiberg-Witten invariant of S1 for some appropriate species structure. So I'm not going to give details here. So basically, you have a homeomorphism, then you can pull back using this homeomorphism. You can pull back homology classes, and so basically, the thing is that under this homomorphism, you get a one-on-one correspondence between species structures on x0 and x1, and they have different Seiberg-Witten invariants. It's true. And so in particular, so that implies x0 is not diffeomorphic x1. We have seen many of such examples in Andreas' talk, like you can take elliptic surfaces and do some log transformations or knot surgeries. Okay? They are distinguished from each other by the Seiberg-Witten. Okay. And the next condition is that there exists a diffeomorphism from x0 connected sum s2 plus s3 to x1 connected sum s2 plus s3. Let's see, and A is a diffeomorphism. Let me call this diffeomorphism phi. Okay. So this is a remarkable result by Wall states that given any two oriented simply connected and later dots prove this and crack prove this for oriented for manifold, given to any two oriented for manifold which are homomorphic to each other, you can take connected sum with S2 plus S2 sufficiently many times and make them diffeomorphic. Okay, so this procedure is stabilization. So doing enough stabilization annihilates all exotic smooth structures. But it's interesting that people in many examples, in most examples, I would say, this exotic smooth structure just disappears after one stabilization. Actually, it's a major open question whether there exists some exotic smooth structure which survive one stabilization. So we don't know that. We know that for manifold with boundary case, but we don't know that for closed domain. Okay. Anyway, so for example, so this is this condition is actually pretty easy to achieve. Say you can set x to be elliptic surface, x1 to be same. What you want is they do like not surgery on this. Okay. And one can prove that after one stabilization, there exists a diffeomorphism. Okay, good. Now let's set this to be a magnitude x. So x will be the connected sum from between s1 and s2 plus s2. Okay. So we are going to construct an exotic diffeomorphism on x. So first we need to construct it, then we need to detect it using family separator. How to do that? So first, we notice that we have an interesting diffeomorphism of S1 or S2, which just says VW to V bar of the bar. Here, just view S2 as one point compactification of the complex plane. Okay, so this is a reflection, orientation preserving, acts as negative identity on second homology. Then we can isotope R prime such that R prime restrict to some small of equal identity. No, this R prime has some this R prime has a discrete fixed point. Well, non-discrete fixed point, but is orientation preserving. So you can isotope that a little bit so that it becomes a diffeomorphism which fits a four-ball. Okay. No longer it's no longer an involution, but that's fine. It's just a diffeomorphism. Then what do we do? So we define F1 to be identity maps map on X1 connected sum with alpha or S2. Okay. We have identity map. So this is X is identity sum. So you can take the identity map on the first domain and take this reflection on the second domain. In order to do connected sum, we need this diffeomorphism to fix a small ball. So that's why we do this isotope. Okay. So this is F1. F2, well, sorry, F0. Well, F0, we want to say that it is identity F0 connected sum of prime, but really that's just that's a diffeomorphism on the left hand side. So in order to turn it into a diffeomorphism on the right side, we need to conjugate with okay. So these are two diffeomorphisms, F0, F1 belongs to this. These are two diffeomorphisms on the same format of X. Okay. Now, it turns out that this phi, there is pretty room of choosing this phi. This phi is not unique because you can always compose phi by a self-automorphism on X. So it turns out that by a result of work, one can always choose phi such that F0 star equals F1 star on the moment. Use the map. These two diffeomorphisms use the same of the voltage. Okay, we can always choose to achieve this. This is by a result. Well, or you can, in concrete example, you can just do that by hand also. Okay. Now, okay. Now our exotic diffeomorphism will just be defined to be this conversation. Okay, this is diffeomorphism.
We want to learn from.
Ah, okay. F1 inverse equals times 0. Okay, so this is a diffeomorphism.
Do you want some B2 plus condition on that side?
Well, okay, so great question. The answer is in this construction, it's okay to have B plus. It's okay that this inequality is not satisfied. You just have to be a little more careful for the word crossing. It's fine. But certainly, if you want to make the argument easier, you can just pick that text to be like E2 or to have bigger B plus. Then it's easy. But it's fine. It's fine to set B plus equal 1. Okay, now yes, so let's see what's the yes, okay, so this is F. So what do we get? So first of all, F star equals F induced identity map from homology. So by a result obtained, that implies F is topological as a public identity. Okay, so it is topologically trivial. Now, in order to prove F is, so what it remains to prove is that F is not smoothly isotopy to identity. How to do that? Well, so let's set E to be the mapping torus of F, which is just x plus 0, 1 proportional by x 0 fx. And of course, this is we get a smooth bundle of the S field. Okay. Now now we can consider, what do we consider? We consider a spin C structure, so consider S to be S1. Okay, this is a spin C structure on X1. And it turns out that we connect this on with this S portion. There is a unique like a torsion spin C structure. Actually, spin C structure with trivial term class on this S2 plus S2. Okay, just the spin C structure coming from a spin structure. We just take this connected sum, and this is a spin C structure. And it's not hard to show that this spin C structure is preserved under, well, because F acts trivially on homology, it preserves every spin C structure. So you can extend this spin C structure to a family spin C structure. That's Furuta. Okay. And now, what do we observe? So let's compute the expansion dimension of this guy. So ES, yes. So this is what? This is P1x squared minus 2x. Okay. Now it's not hard to see that by doing this. Okay, so let's see what happens. So we take a connected sum with S2 plus S2, right? So okay, so what does that do? Okay, that doesn't change the signature because signature of S2 plus S2 equals 0. But that increase B plus by 1 because B plus of S2 plus S2 equals 1. And that doesn't change C1 squared because we are taking connected sum with a torsion spin C structure. So C1 squared is unchanged. So the conclusion is that this guy equals P plus 1 minus 9. So the expected dimension of the moduli space on a single fiber is -1. And that means P as Furuta is -1 plus 1 in the group. Because the base is S1. So the base dimension compensates this fiber dimension. So that's 0. Okay. So that means FSW of this PF as Furuta, it's a number. Okay, because the expected dimension is 2. Now, what's this number? Now, how many rounds? There's a non-trivial theorem, which is essentially a Gluing theorem. And also later general follow. Says that is FSW, PF as Furuta equals Seiberg-Witten invariant of x1 s1 minus Seiberg-Witten invariant x0. Just equals the difference between the two Seiberg-Witten invariants. In particular, since our assumption error is 0. Okay. So that means ES still not figure, figure. And let me dive the bottom. It's not symmetric. So meaning that there does not exist a diffeomorphism from this to x1 such that this diagram fits.
Yes. There's a statement, or we need the statement that x times s1 has trivial family Seiberg-Witten.
Yes, that's basically that follows from the fact that if you have a trivial bundle, the family Seiberg-Witten invariant is 0. This is actually easy to see. Why is that? Because for trivial family, you can just pick a constant family of metric and perturbation. And because this condition, because PS equals -1 for generic family perturbation, its modular space is just empty. And since you can just pick this constant family, you just get empty modular space. So the Seiberg-Witten invariant is 0. But essentially this is a Gluing theorem. This Gluing theorem tells us that whenever you have a decomposition of a bundle into two pieces, one piece is basically this x1 bundle. The other piece is this S2 cross S2 bundle. Where you are doing like this kind of fiberwise connected stuff. This Gluing theorem tells you that the family Seiberg-Witten can become the Seiberg-Witten invariant of the file. And so that is a sketch of the argument. Yes, okay, so when do we start?
At 46.
Oh, great. Okay, so I thought we started at 30, so I still have like great. Now let's talk one more application.
Is there something about this expected dimension versus dimension as well? When the expected dimension was negative, it could be 0.
Yes, okay, so let me explain this. Okay, so let's consider this case. This is a set saying that the dimension, the expected dimension of a single fiber is negative dimension of the base, and this is less than 0 because the zero base is positive.
Yeah.
And what does that mean? Okay, so let's say you have a fiber bundle. We pick a generic family metric of family metric family configuration. This condition tells us that on a generic fiber there is no solution code because it's on a generic fiber we are taking a generic metric and generic relation, so there's no solution at all. But on some, but here we are thinking about a whole family. So on finitely many fibers, there are some solutions that comes out. And this family Seiberg-Witten invariant is actually just counting these solutions. And this also tells us that if we are taking the trivial bundle, the family Seiberg-Witten invariant is 0. Because in this case, we can just take GeoTop to the T for GB, that you just take the constant value of metric and the constant family of integrations. Then if we take the generic G and generic beta, then the whole family moduli space would just be empty for trivial. And so that's this you can say this as one. Okay, here is a alternative description of this story using the homological refinement. So maybe let me talk about that. So Tom talked about this proper Fredholm map. Turns out that this as one can also package this family Seiberg-Witten invariant into a one can also package this family Seiberg-Witten map into this map SW2. So I just erased. It's a proper Fredholm map. Okay, it's a proper Fredholm map. Then by doing something called finite dimensional approximation, which was mentioned yesterday, one can also solve in Thomas' talk. So SW is proper. So by doing finite dimensional approximation, this gives us a map approximation is like a map goes from Tom space of V1 to the Tom space of V2. Maybe V plus V2. I need to explain this terminology. So V plus V minus, these are vector bundles on the face, which fibers are just with some. Okay, it's a vector bundle over the base, and this you can do finite dimensional approximation. If you have a proper map between two vector bundles, you can compactify this map and get a map between Tom space. Right. That's for finite dimensional setting, but in an infinite dimensional setting, because you have this proper Fredholm map, you can do finite dimensional approximation and get a map between two Tom spaces. Okay. The important feature of this Tom space of this vector bundle is that if you take this virtual bundle, this equals the index of this Dirac operator Dirac sum plus this family index. This family index. Okay. So that's the element. Okay. Then we have on each fiber we have the Dirac operator, which is a Fredholm operator, And on each fiber, we also have this Hodge operator, which is another fractal operator. So you can take an index bundle, which is a virtual bundle representing an element in a K group of the base. And the thing is that this approximated Seiberg-Witten map give us a map between these two Tom spaces, and it is S1 equivariant. Okay, and you can view it as this is S1 equivariance. Okay. Now the stable homotopy class of this SW ATR. Here S1 acts as like trivially on this component and acts as scalar multiplication on this. Okay. This represents an element between this Tom spectra and this H plus. Here is S1. Okay. So, and this is there was a sort of family Bauer Furuta invariant.
That's actually a tail.
Oh, okay. Yes. Yeah. This is real. Yes. 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 So we put this S1 here. So it's a S1 equivalent stable homotopy class between these two Tom spectra. Okay. So this is a virtual bundle. So we really need Tom spectra. This is an invariant of this E slash E as theta. Okay. And basically, what does the family Seiberg-Witten invariant do? You take the zero section of this is a Tom space because this is actual bundle. This is an actual bundle. Okay. You take the zero section of this Tom space. You take the pre-image. Wow. Okay. Yeah. You take the pre-image under this Seiberg-Witten, and under this oh no, sorry. Okay. What I do? What should I do? Okay, so let me just say that. Okay. If B plus of X is greater than the relation of B plus 1, then FBS S1 recovers the family Seiberg-Witten invariant. Basically, you just do this. You just count certain mapping degree. Okay. This is not the case if B plus equals or B plus less. In that case, the work property contains some additional information which is not seen from the stable homotopy refinement. Okay. For example, if you consider the Bauer Furuta invariant of CP2 blow up sometimes, it's always trivial for some trivial reason. But the Seiberg-Witten invariant is not trivial. That allows us to detect exotic CP2 blow up 2 times, 3 times, or 6. Okay. It's actually because B plus equals 1. Okay. Anyway, so now let me also there is also one can also interpret this. Okay, this is S1 equivariant stable homotopy class. We can also forget about S1 equivariance. Just treat this as a stable map between these two spectra. Just forget about equivariance. That gives us the usual family of Furuta invariant, the non-equivariant version, And this is by the projecting Hom construction. This is more or less just a frame homological class of Seiberg-Witten morphisms. You know, you have a moduli space, you can by the yeah, you can either you can consider it carries a canonical framing, or really stable framing, and you can study the stable framing homological class. That give you the very powerful time variant. And normally and dominance or mentioned the other application of this small Furuta, which is another exotic different. So we let X be H3 directly signed into. Okay, let's take two copies of H3 surfaces and let's design together. And now, okay, so one thing, so a natural thing to do is you can consider this F from X to S, which is the gang twist along this connecting neck. What does that mean? That means F equals, okay, so we decompose X into three parts. This is function P3. This is 0, 1 plus S3, right? So what we'll do, we'll define so delta equals restricted to 0, 1 plus S3 since theta X to theta R theta. So R theta just means the rotation. With rotation of S3. Well, maybe I should put 0.6. We use this rotation. Then also this equals X minus is 0. In other words, it's a band twist here and identity here. Okay, and I'm sloppy here because we need to slightly cut off to make this smooth near going part. That's okay. This gives us a diffeomorphism. It's not hard to see that it acts trivially on homology. So again, by Quinn's theorem, this is the X delta is athletically isopropyl identity. Okay, but surprising theorem by Peter and Tom was found. Says that this delta is not smoothly isopropyl. Essentially, is not smoothly isopropyl to identity. Essentially, because the family called Furuta invariant of this mapping torus is represented by eta squared. Eta here being proximal. Eta squared eta cube. Oh, eta cube. So cube. So therefore, this is on our that you can. Our is just P3 is equal to in particular, this represent a non-trivial element in a frame homological group. So the family of Furuta invariant is non-zero, that means the monodromy is not smoothly isopropyl to identity. Okay. And here you can see that this is a result which cannot be seen by starting numerical Seiberg-Witten invariant because it's Hopf map is partial. So you cannot get a we cannot detect a portion element by starting an integer value in there. Okay. Yes. Okay, so yeah, I think that's one second. Great.